And welcome back. This time we're going to be looking at how we take a function and wrap it around the y-axis and make some kind of three-dimensional object out of it. We're going to be looking at the method that uses disks that allow us to kind of stack them up and take the volume of each disk, as it were. We'll be using the same integration methods that we have learned so far. So let's take a look at a general case and what we have. I'm not going to be using so much numbers as ideas and general functions and how they work. So let's just take a look at what we have. I've drawn out here y equals f of x, and just a general one. I just went ahead and drew it up like that so that we could get the idea of what we're doing with. And then after that, we'll take the general rules of what we need to do in order to analyze it. So these yellow lines here, this D and this C, they are where we are saying, okay, we're going to analyze this or create this volume from wherever C is. Sometimes C goes right through the 0 point, and that's fine. But this one, for the purpose of illustrating, I have it a little bit above that. D is just the place where we're going to stop. And it'll be this part here that we then wrap around into a kind of bowl when we're done. And fortunately, I'm going to let the computer do the wrapping because, as you all know by now, I can't draw to save my life. So let's look at what we have. We have y equals f of x, and it can be anything. You know that by now. F of x has so many different ways of looking, of behaving. We're going to take a classic function. This one looks to be similar to a second degree function. And let's see what happens when the computer draws it out. That's a lot better. Okay, what we're going to do then is I went ahead and put in the dotted lines for the D and the C there, and you can see there's a tiny little disk down here, and that little disk is what is giving us the bottom of our bowl. And up here on the top where D is, the line y equals D, is the rim of the bowl. Now, what is it that we need to do? Well, you see in your book there's a formula, and it looks like this, but you're probably wondering, well, how did they get that? And it looks awfully scary. So let's take another look. We'll try to draw these little pictures and do it piece by piece so that it doesn't look so bad. If I take some x, so as long as it's still in the domain of this function, it could be anything. It could be 2, it could be 3, whatever. I'm just doing this for the purpose of illustration right now, but I think it'll make sense in a moment. You see in here, there's a new little blue disk right here. It has a radius that is x. That's where we started from there. Say x might be 2, it might be 3. I mean, it doesn't matter. It's somewhere on the x line, and it's within our domain. And this part right here, where I made it dotted, that is the part that is the radius. So if we were going to draw a disk, say any general disk at all, they have a radius. And if we wanted to make, say, a CD, you know, a CD isn't two-dimensional. It actually has a thickness. And what would we need to do for that? It's, okay, sure, a CD isn't very fat, but it still has some kind of height. And that's around the whole disk there. It's a wafer. All right. So if we're looking at this as a series of disks, say down here where C is, That's kind of a small disc at the base of the bowl. And then we could put another disc on top of it, and it might be just as thick, but it might also be just a little bit bigger. We could, at this point, we can just say all the discs have the same thickness. We could say we have a bunch of CDs, and some of them we cut a little bit on the edge. So it's, instead of, I don't know, 20 centimeters, now it's 15, and one that's 14, and so on. And we could just stack them all up. And then if you could count the discs individually and say, okay, how many do we have? What does each volume have? You would be able to get a pretty good estimation of the volume of the little bowl that you made. In essence, that's what we're doing. But the discs that we're going to be doing aren't going to have a decided thickness. Their thickness goes towards 0. And that's where the whole limus came from, the limit, as the thickness approaches 0 of this particular function and the disk that it represents. From that, we can then add up these infinitely thin disks and their volume and get something that is much, much more accurate than just adding up some CDs where we know, okay, each one is 1 millimeter thick and so on. These, they get paper thin and then thinner than paper, and we stack them all up and we get a good estimation. So as you know, regardless of how thick the disc is that we're playing with, it will have a thickness. And we need to just rewrite the formula for the volume of one, which is the normal ones right there. And we need to rewrite it so that we can have use of it in our integration. So that's why we have the dy here. Because as you see, the disk, even this one, it's going to have a thickness, but it's going to be dy thick, okay, instead of h thick. So it's still very similar to what we're used to. It's just different when you wrap it around the y-axis. If you can wrap it around a y-axis, it's almost always easier to wrap it around the x-axis. But we'll be doing those too. But I prefer to start this way because then the next step's always easier. All right. With this general formula, if you look at any of the disks, let's just take that one. What does it have for its thickness in this case? Well, there we have that. We see that we have a radius, that's x. And what is that? Well, that's x squared, because what do we need for a disk? We need pi r squared. R is x, h is dy. And then when we integrate, we can take pi outside of the integram because it is a constant, so it's not going to play any role. And what you'll see is that, in essence, this means the sum of all the disks that we have stacked up, each little disk having a volume, and we take it from C to D. So you'll have an infinite number of very, very, very thin disks that we then, through integration, add all up. And then you get a nice pretty bowl, or whatever. We can get a donut, we can get a sphere, we can get a cone. So in the next one, I'll be showing you how to wrap a function around a simple linear function, wrap it around the y-axis, and get a nice cone. And you'll see that it's just like the volumes that you remember from, I don't know, Math B or something. So, all right, next time we'll be doing part 2, and that's going to be with a cone. All right, I'll see you next time then.